Okay, so thank you so much for the invitation again. It's mine and everyone. The title of my talk is Wireless Communication for IoT in Water Environment. Before speaking about the talk, the technical, I will present myself. I am Miguel Gutiérrez Gaitán. I have a doctoral degree in electrical and computer engineering from the University of Porto and a Master of Science in Telecommunication Engineering from the Polytechnic University of Turin in Italy. And in Chile, I have a bachelor in electronic engineering, Ingeniería Civil Electrónica, from the Universidad Católica de Valparaíso. I work in telecommunication from last, I would say, almost 15 years. I'm not that young. I started as an intern in Telecom Italia when I was doing my master. Then in Chile, I worked for Huawei. I did RF planning. I did microwave design. And I entered the university with this, mostly teaching. But I always was fascinated by the idea to do a PhD and do research, and I'm doing this now. And in the last 5 years, I was living in Portugal. I did my PhD in Portugal, particularly at University of Porto in collaboration with the SISTA, which is a research center in real-time and embedded computing systems. And during my stay, I also visit INRIA Paris. I visit the lab of Professor Thomas Watain, which is a very famous guy in IoT, and we still have collaboration. And then I'm back in Chile because I keep my contract at the university at Universidad Andrés Bello. Universidad Andrés Bello is a private university, is the largest university in Chile in terms of the number of students. It has a campus in Santiago, Viña del Mar, and Concepción. It has good ranking. It's a very young university, has only 35 years old. And for example, it's the fourth now in the Shanghai ranking, which is an achievement for them. Particularly in electrical and computer engineering, we are new. There is a bachelor program in electrical engineering, which is just 2 years old. And I'm also leading a bachelor program in cybersecurity engineering, which is also 2 years old. Still, I would say in this area is growing, although they are very strong in areas like astronomy, medicine, and as a university and those kind of areas. So more about the collaboration networks I have. So I have very strong partnership with the place where I did my PhD. They now invite me to continue with them as an international collaborator. So I keep collaborating with them, and in fact there are 2 papers in this conference which I did in collaboration with people from Portugal. And still work with Thomas Lab in Paris, and we're applying for funding as everyone. So if any of you like this kind of research that they also do, so I can be in contact with them, and we can try to collaborate. And in Chile, I work mostly with the Universidad Diego Portales and with Professor Diego Duovne, and currently with the Pablo Palacios, which will be here today. And I have a PhD student and Universidad Católica de Valparaíso, which is working in this topic, like in other areas. So I would say that is growing in this research. I also very active in volunteering. I am the president of the ITB ComSoc Chile chapter. I collaborate in the global conference also for ComSoc, and a lot in ITB Future Network, which is not a ComSoc related, which is involve many other communities. And as a TPC, I typically also support conference in the special interest group in embedded systems, and all that are related with industrial communications and real-time systems. VLC, I would say, is a topic which is there too, but sometimes not seen in the same perspective. But still, one of the papers that is here will show some of these intersection that could be interesting for your community too. So this is more about my. This is all more or less about my biography. My areas of interest are wireless network, real-time communication, and Internet of Things. I mostly teach and do research in this, and I have two line of research which I feel very independent. One is radio frequency propagation in overwater environments, and the other is deadline-based wireless communication, which is related with the real-time concept in the real-time system community that I will explain later. Still, the focus of this talk will be the overwater part. Okay, so now we will start with the technical aspect of the talk. The challenge, so the agenda is pretty simple. I will introduce the topic. I will divide the talk in two parts. One is overwater communication, which will be the focus, and then real-time communication, just as a very fast topic to make you aware of what is this area. We started in a project at the beginning of 2018, more or less, and we were seeing that the growing demand of IoT and industrial IoT and wireless communication in water environment. And we say, okay, this is not new. So wireless communication in water environment has been from the beginning, but there are or not new challenges here, and then we start to observe that IoT was something that was growing, but not necessarily in overwater environment. What are the differences that brings IoT in this environment? Particularly, wireless links are typically short to medium range distances. Also, the antenna height are low or even very low. And this, although it looks, I would say, like not a problem, it is from the perspective of the water. Water dynamics are in the order of these distances and heights, which creates a new challenge that I was addressing during my PhD, particularly the effect of tides that looks sometimes not a problem. So from the point of view of the dynamics are very slow and typically are ignored, tides, but the differences of, I would say, a few meters in the order of antenna height, you will see that might create issues, and this we were verifying this issue in the field, and all of this adding the complexity of IoT, and not just IoT, industrial IoT, which has periodic traffic, maybe has deadlines, so time constraints, and even missions that could be critical. So we started to say, okay, what we could do here, and I would say, okay, let's try to address this topic in an integrated way. And then it was not easy to make real-time and overwater together. So we were starting doing, I would say, the simplistic way. So let's separate this problem. We will first address physical layer issues. We will address overwater communication, and then we will go through the other, I would say, layers. This can be, of course, studied from an integrated perspective. Cross-layer issues exist for a long time, but I decided to do this separately. So what you will see first is the overwater communication, physical layer, and radio frequency propagation, with the focus of studying the one of the aspects, which is path loss or large scale failing. So let's start this. I would say it's important for students. Let's start from the very beginning. So I started as a student, say, okay, what I can do here? What are the models? These models are still valid or not? And I started with the very first model for overwater environment, which is called the two-ray model. I was reading the literature, and the literature was not clear about the usefulness of the two-ray model for IoT. Two-ray model is extremely useful for ship-to-ship communication, from short to ship communication, maritime communication, where the towers can be 5 meters, 50 meters height, and distance are typically kilometric. But in IoT, we were not having this. So what literature was saying, and literature was saying that there is not match with the two-way model. Since I was curious about this, I was working in telecommunication before. I did RF. I said, no, this should be something here. So and what I feel which simpler was useful from the two-way model. The two-way model has just two rays, so it's very simplistic. It's representing the attenuation just with just two vectors. But one of the vectors is changing according to the water level. So we might be able to model the impact of water level in the attenuation. So we start doing very first simulation as everyone is doing when starting the PhD, and we say, okay, well, there is something here. This is very simple. This is all the books. And we observe that, yes, there are things that no one is taking into account. Look at this. This is a power received versus distance. Power received here as for a shore-to-shore link. You have the transmitter on the left side, the receiver on the right side, and we have the wire. And we say, okay, what happens if these transceivers are fixed and just the water changes? Let's say that it changes just 1 meter. Should be exist something, a problem with this 1 meter? Heights are the 2-3 meters, and we are using Wi-Fi with 2.4 gigahertz. So everyone is doing it. And the third is, which is the plots here. So in the red line, you see the plots for the link when consider both heights are at 3 meters, the red line. And the blue line is when both transceivers are at 2 meters from the water level. So this can be seen as the heights are fixed, but it's the water what is changing. So it's the relative height from the transceiver to the water, which is changing. And as you see, we say, okay, look, the density of the nulls or the deep phase is changing. It looks like the red curve, which is the higher height, has more nulls. So within a distance, within a given range, it looks like the higher height is worse. And of course, there is a complementary behavior. Look at this complementary behavior. You can see what happens if I have two heights, one at two antenna heights, one at one at 3 meters, another at 2 meters, and the water is not moving. So we will have the effect that is known as space diversity. So this can be useful for tides, and this is known that is useful for tides. But we also see that the deep phase or the nulls or this attenuation is also moving, and then there is the peak that in this non-linear behavior is also moving, which is called the breakpoint distance. So we say, okay, there are many things to explore. Let's see if this makes sense. And I say, okay, let's try it. So let's see if this is working or not. And this was the second paper. The previous was the first paper of the students, like trying to do things. Then second paper, let's see if this is going to work. And we were doing this in a very simplistic scenario: Wi-Fi, a tripod, an antenna height, and transmitting beacons for different distances. Here's the setup. And what we observed was, I would say, revealing. Look at here, the blue line is the scenario for is the results of the received signal strength indicator for two transceiver at the same height but at 1.45 meters. And the red line is for the same scenario but when the antennas are higher, 2.45 meters. So what was I would say, for a student is counterintuitive, or even for everyone. I say, okay, look at these results. The higher height has worse results. So it seems that you are not, when you have a signal problem, you are not putting your antenna higher. You're putting your antenna lower, and you are getting better results. Still, we were not observing the two-ray model like exactly as we expect. If you see, the two-ray model is behind, is with a dotted line, and this says that there is the relationship looks similar and the results suggest a null. But we are not seeing completely the two, right? But we received very good feedback from the conference and from everyone. And they will say, we are saying, yes, but this is just 5 dBs. And then there was people there in the community saying, I'm doing design for 5 dBs. I am doing antennas just to improve 5 dBs. So this is a good result. And then we said, okay, for us, this was not much. And so as a student, I said, oh, it looks like my research is interesting. So I said, okay, maybe let's use these results, and I started to do a very initial design. So we were designing antenna heights that were dependent of the tiles moving. And we were also saying, okay, let's design also the position, because if this model is valid, maybe we are going to see something. And the design is mathematical and nothing complex, sorry. And basically we were adjusting the antenna height according to the movement of the water level. Because tides are cyclic, so we can, if we know how the tides are moving, we say, okay, let's provide an antenna height that is best for this particular tide. So it's a tidal informed design. And again, we say, okay, let's see these results, and the result says, okay, here these are more not very common results. So you see the average path loss here are lower is better in the plot, and in the x-axis you have the antenna height. So the antenna height has a fixed range from 2 meters, from 4 meters. So basically we have a pole, and from 2 to 4 we can change the height. Which height we are going to choose? And we will choose the one that provide in overall the lower path loss. And we were comparing against what was the state of the art. So state of the art was a very basic state of the art. State of the art was, if you have a pole that is 4 meters high, where are you going to put the antenna? Put it at 4 meters. This is logic. You're not going to put it in the middle. So we said, let's see. And we were seeing that putting it according, knowing the tides, putting it not at the top, we're having lower and all very similar results in terms of path loss. And then we say, okay, and what happens if we use 2 antennas? Because 2 antennas is always used as space diversity for mitigating tides. But also the book said use 1 antenna at the top and another at a particular spacing based on the lambda, based on the, how do I say this in English? Sorry. Wavelength. Based on the wavelength. So we were using that book, and I said, okay, look, yes, the results we achieved here, H1 are our results, and H2 for the second antenna, and H1, so 4 meters and 3.64 meters are from the for the classical approach. And we were having better results with lower antenna. I would say, what is good about this? Well, a shorter antenna height is not only cost effective, it's also more robust, typically against wind and other things. Well, still these were theoretical, and I would say I was studying, and I said it looks interesting. Let's try simulations with another scenario, maybe buoys, maybe stationary nodes that are floating, that need to adapt their height, their distance. And we observe here that the path loss, the positioning can also be adapted according to the height. So here you see the path loss when sorry that there's an issue with the visualization. So the red line is considered. What if I do not take into account this approach and I use any height? So the worst that I can get is the red line. So, and what if I use the top, the top antenna, which is the common approach, where I get the yellow line, and this of course based on a given tidal cycle. So what we are saying, okay, we can say it looks like 20 dBs if we put an antenna height and a distance that is convenient for our design. Still, this is theoretical, and then I said, let's try to do this in practice. So we were lucky that the lab close to our lab was this lab, which is is a huge lab, which is subaquatic systems. They developed this very expensive system, and we talk about them. We show our research. We say, let's do it. Great. Let's try if your design it makes sense with our system, real systems. And these real systems at the beginning were very challenging because they show us underwater vehicles. So the vehicle goes under the water and goes to the surface to transmit to the shore. And transmit to the shore with using which technology? Wi-Fi. And which frequency? 2.4 gigahertz. And what is the antenna of this? This is 17 centimeters. 17 centimeters, but the wavelength of this 2.4 gigahertz is 12.5 centimeters. So I say, sorry, I don't think we are going to see anything. So I don't know. I was curious about this. So let's do this experiment. And here I would say that we were very excited seeing this. So we were seeing the effect of the nulls. We were seeing the effect of the Q rate very clearly, just using Wi-Fi frames. So we were not using channel sounders or all the other typical propagation equipment. So equipment that are used to see this. We were seeing this with Wi-Fi packets. So what you see here are all the Wi-Fi packets for a campaign of about 15 round trips travels from with using these underwater vehicles, which was going to the surface and transmitting to the shore. So here again, it's a similar contradiction or counterintuitive results. So we were asking them, what do you do when you finish your mission under the water and you need to transmit this to the shore? And they say, of course, I will go to the shore as close as possible because I wanted to transmit with a higher quality. And we were showing them that the higher quality is not as close as possible. As you see here, we have almost 40 dB differences in Wi-Fi, and then there is not a steady behavior. So our approach here was saying, okay, so move then to a more favorable situation. Then the feedback from propagation people was saying, okay, yes, this looks nice, the trends are good, but look, this is not the same. Look, there's a difference here. I say, yes, there is a difference here, and we are working on this. So we can still improve this model, but this is already very good. This already can guide design of state-of-the-art research. So high data rates and not just the future of, I would say, we need to try this. We are one of the students, I was saying, the PhD students, what is working on this is working in millimeter waves. With we want to test this for higher frequency. This is going to make sense or not. Still, for the scenario where this is used, this is I would say this is useful. Then this is just one scenario of IoT. So we were exploring. This was not our first focus. We were looking for a collaboration with conference with colleagues, and then another approach was using classical IoT technologies. Now are classical, although they are recent, like LoRa. And we have a particular scenario here, which was an estuary, estuary waters, where rivers arrive to the sea. And they say, okay, but estuaries are not like our scenario that we're looking before. Starting gets dry. So we have flooding, and then we have the reverse effect. And this reverse effect is going to show dry areas, or this terrain that is as you can see here in the next slide. So we will have the shoreline that is moving, we have the water, and maybe we have different terrain profiles. So maybe the two-ray model is not going to work. So we propose a methodology that try to convey in the simplest way, in a very simple way, the space, the spatial features, the temporal, because this is taking into account the tides, so this is happening because this is a more or less predictable behavior, and the physical features. So this is water, this is terrain, this is wet or dry, and we were using LoRa for a scenario given for a research project. That was a national project. And look at here. So we noticed that something that we were ignoring before was the reflection point. We were ignoring before because the water is flat, and I don't care where the reflections it's happening. But here it's not the same. So we are having areas where it's dry, where it's wet, and so maybe this is going to be make a difference. I didn't know it. And also there is a terrain profile, maybe 10 centimeters, 1 meter different in terrain profile. I don't know. So we here we partnered with a lab of an engineering civil engineering lab that they have hydrodynamics models. So they provide us hydrodynamic models of bathymetry and water level for the location we were stuck. So they provide us a simulation. They didn't understand what we were doing, what is signal, what is error side. They just provide how is bathymetry, so this is fixed, this is terrain below the water, and how the water moves according to a very, very precise model that they say to have. And we were tracking the reflection point according to the heights we were studying. And we integrated all of this is a new methodology. So we considered the tidal model according to what they were saying, their reflection point, and then at the end we were using the two-ray model. Two-ray model same as before, but now taking into account a parameter, which is the parameter that we were ignoring before was the relative permittivity, the dielectric constant. This parameter is important because the permittivity of the water is different from the permittivity of a dry soil. But and we will have to study what happened in the middle. So what happened when it's not dry and when it's water. So we were using again very simplistic approach. So we say, okay, water is known in this value is 81, and terrain is also known as the value is 4. But in the middle, we have to look at the literature, and we found that the literature say that okay, when the water content is increasing, there is an exponential relationship. So we were using this model. And we put all of this just as a model. So we have here the result of the heights, transmission power, the distance, all the data we have, and we thought, I hope that we are going to see this. And the results were again enough, good. Again, there is not a perfect match, but you can see here, so on the top, this is the model. This is the model provided by our methodology. The methodology predicts the changes according to the tides and even other little effects related to the permittivity change. And below you will find the real world measurement, so with LoRa equipment, and we believe there exists a relationship with this. We are not here looking for accuracy, we are looking for trends. And this was good because the state of the art was saying nothing about this. We're saying this is a line. You need to don't care about this. And we are showing that this, you need to care about this. And we are still pushing here. We have a collaboration ongoing. We are trying this same idea with this feature over water. And this is under submission. And so we are continuing this research, and this is also for us interesting. So that's why I'm showing this result here. And these, I would say, were the most interesting results I got recently from the overwater part. But as I said in the beginning, IoT is not just overwater, and so it's not just the physical effect. We can also have data link effect, network layer effect. And here I also got interesting result from the point of view of the network layer. From the point of view of network design, so this is a cross-layer approach in which we try to look at high reliability and low delay, which is very popular nowadays for the time-critical IoT communications. And in the community where I work, which is a real-time community, this high reliability and low delay is integrated in a metric, in only one metric, which is called schedulability. So it is the ability of schedule packets in a predictable way. So I was using model that I proposed at the beginning of my PhD when I was exploring different areas. So this is more computer science related, and we will consider here mesh networks. Mesh networks that are like based on time-triggered communications, multi-channel and TDMA, and here is the model. This is not a very simple model, but we were using what is considered the state-of-the-art in scheduling for real time. State-of-the-art for scheduling real time is earliest deadline first. It's a state-of-the-art because it provides the best results in terms of usage of the bandwidth of the capacity. So we were using this as a performance model. What are the contributions here? So we were saying, okay, let's assume that we designed all the overwater links in a way that was robust, where there is enough reliability to have a stationary, I would say, topology. We can use more than 2 antennas. But then what happens? What happens if we have periodic transmission and we have a mesh? And we found that it was not in the literature, it was not clear where to put the gateway. Everyone was working on the same topic, where it was scheduling, routing, scheduling. And then when you ask, where do you put the gateway for improving the real time, there was not an answer. And this was our best working progress paper award, in which we showed this detail and saying, you can still improve the communication, the real time communication, which is based on meeting deadlines, by putting this the gateway in a particular position. And we were using data science techniques that are very popular nowadays. It's based on social network analysis, and we use the most common centrality metric, which is the degree centrality. So it's basically saying degrees is saying how many nodes are neighbors. This is degree. And the node in the mesh that has more neighbors, you will choose it as the gateway. But there are other metrics like betweenness centrality, closeness centrality, or eigenvector centrality that use more complex approaches, like I would say the spectral property of the network. And in any case, this was the first paper in this line, and it was saying that okay, this is good idea. So we continued pushing this idea, and we say, okay, let's move now for more gateways. So what happened if we don't need one gateway, we need 2 gateways? And say, okay, but the centrality metric is choosing just one, indeed. So we cannot choose how do you use this for 2? And we say, let's use clustering. Clustering is we can divide the network. And they say, okay, but clustering typically uses distances. We are just having the topology. And then we discovered that this is spectral clustering, a very popular approach from these guys that are developing the state-of-the-art algorithm for machine learning. This guy NG, and we use the spectral clustering first to divide the network according to their properties, so the topological property, and then within each cluster we use our approach based on centrality. So again, the results were good. These are still simulation. We got high improvement in terms of the model, and then we say, okay, but these centrality metrics are not made for this particular scenario. So we say, yes, indeed, we can still improve this metric, and we propose a new centrality metric, which considers the effect of in mesh communication. You have typically half duplex transceivers that cannot receive and transmit at the same time. So to provide this joint path is something that is useful. So we propose a new minimal overlap centrality metric for this particular mesh topology, and this also was an award in a workshop. We got an award in a workshop organized in the United States, and then we are still pushing this approach, and we also got good results. The problem is here at the network layer, because it's still, this is related with routing. In the end, it's related with routing, so we can still then not change the gateway position and also use the routing trying to copy the same behavior. And again, here we propose a new heuristic, so based on local search, and the heuristic was also good. So what is missing now, and is part of an ongoing work, is putting everything together. So putting the routing, putting the centrality, and also this global EDF scale. And we are pushing for a real-time framework. And I would say that the challenge here is, let's go for real work. And I was lucky that the guy that I was in France was Thomas is chair of Stitch, which is the model we were using. So we were using the model for TH's network, and he liked his approach. He said this is valid. We are going to use it. And one of the direction is use this now for robotic swarms. He has a project which is called Open Swarms, and now we can adapt this model for robotics, so that I'm moving, and maybe so that instead of selecting a gateway, we can select a leader, and this is one of the direction that I would like to take. And this is more or less the two line of works that I have worked recently. Physical layer, network layer. If you feel that there is something that you find interesting, if you want to trigger collaboration, I'm very open to do that. And of course, there is future work that is not just the layer I was ignoring. This was detailing layer, but there are challenges in terms of how to do this online, how to do this offline and online, how to provide low power, how to provide adaptivity, reconfiguration. And I have some work of this level, but they are not yet that mature to show here. But we are working on these ideas. So thank you so much.
Thank you, Miguel. Questions about the presentation?
Thank you. Thank you, Miguel, for your presentation. I just wanted to say, I invite you like an example of what I was expecting to get from university when I finished my degree. I see how you're doing international collaboration, volunteering, teaching, experimental research, industrial involvement. Like for me, and I think for the students, it's the way to go. But I'm curious about which one of all these areas is where you have felt most comfortable. And if you had like a magic wand and you only choose one of them, which one would it be? Thank you very much.
Thank you for the comments and appreciation of the work. I honestly, I like ideas. I like progressing ideas. I like reading a lot, and I like writing. So which is a strength. So when you put these ideas into words, I like to do that. And here, what ideas I chose was ideas that you need to convince people. And I don't know, someone is trying to write a paper, you need to convince people that this is valid and it's true. So I would say that I would like more the process than the actual area. And I would like to do this process also with VLC. So I'm curious about VLC. I'm outsider in VLC. We have two works here in which I'm not the main contributor. But then I'm learning, and I see that there is potential to do this RF. For example, with the CES and Pablo, we have talked about this. So there is this water to underwater communication. So here's overwater, but RF doesn't propagate through the water. So we can use VLC for that. So that could be a very interesting direction, but if nothing is related to water, we can do this in other domains. I also have a line of work which is in vehicular communication, B2B communication. We are working in two-ray modeling, effects, so similar effects about nulls, but in B2B communication. So I would say that I don't have a, how do you say, favorite song, a favorite. Just the process, and I like to study and do research. This is my approach.
Thank you.
Thank you, Miguel, for your presentation. I've got a few things that we need to discuss.
Thank you.
If you take your first model, reflection of the wave on the surface of the model, the surface of the wave. If you imagine that water surface is flat, yes, so you get one bounce, and then you look at the C signal, which is line of sight and line of sight. Just look at it.
Yeah.
Added power. And when the wave is moving, then you have amplitude fluctuation.
Yes.
So therefore now you have three vectors. One is the line of sight vector.
Yeah.
Second vector is the non-line of sight. And
Yes.
the third vector, which is actually the first two vectors you added up, you get single vector.
Yes.
And then on top of that single vector, there is a third vector, which is related to the amplitude fluctuation, which is amplitude induced noise, because the wave is moving around up and down and it goes sideways. Did you actually consider in that manner, and therefore you predicted the SNR, signal noise ratio, as a function of the behavior of the water level, the way it is choppy? Yes. Did you look at that in your model, and or even to get some early indication that how does this vector floats around?
Yes, yes.
Summation vector?
Yeah, I understand. Yeah, I read a lot, and the literature also is also talking about that. And there are further effects for some of this, even the evaporation ducting. So there is a third rate that typically appears too. And this is I would say that it can be integrated with this, because this is pathless. This is not yet RSNR. This is just RSSI. So we are not even considering the effect of interference. But where this is more clear, I would say this is here. So we have here fluctuations. There are models that can model this fluctuation. What is difficult is to model the fluctuation at this kind of level. So we have the 17 centimeters antenna. And all the models are not describing this for our approach. So it still didn't look at that completely, but this is a valid and interesting and complementary research that needs to be done. So I need to see if the existing model, for example, are useful to maybe predict this change here.
Which this one I can understand that, and I can even see why you have this massive gap between your two-ray model, which is the most fundamental model.
Yes.
And then your measurement is telling us differently, because what the receiver is capturing is many reflections from the surface.
Exactly.
Whereas your model is only considering two. If you extend your model and
Yes.
randomly many different paths, you will approach the top one. You must approach the top one.
Yeah, I understand. Yes.
My question was that did you in your previous, because this is many years.
Yes.
Did you look at the SNR and the behavior of the noise?
Yes.
Due to this amplitude variation, because it's fantastic.
Yes.
Because the wave does
Yes.
move around. So you need to see that how this SNR changes.
Yes.
Depending on the weather condition, either how choppy is the water.
Yes. No, I didn't look at details. So just think about it and justify and say, okay, this is not important now. Typical excuses to do other things, but not at that level. But I feel I also think this is of course interesting.
My second point is that in a when you move away from line of sight, the important thing to look at is a delay spread.
Yeah.
So that decides that how much packets you can send through your network. Did you guys study the delay spread in this sort of environment? So therefore it gives you the boundaries, the limits of your data rate.
No, I would say that it's also formative. So it's because of differences in doing research. So I have colleagues. One of the colleagues I work in this direction. So he have suggested to do this, but sometimes requires time or require our students. So we didn't find yet the students or the time to do that.
Yes.
But yes, these are directions. There are still more directions. I think what I like of this research line is that we have found something that you can do a lot of research.
Yes.
There are still things that we don't have answers. So yes, what I forgot to say is that we have a paper and we were modeling the moving of the vehicle. So the tilt, for example.
Yes.
So the vehicle is going, and then when it turns out, there is a null, not because of this effect, because there is an occlusion, because the antenna is moving. So we were going, instead of going to that direction, we went where we felt more comfortable in the sense of deterministic path loss and radiation patterns. So this is one of the directions. But completely agree that there are other things to still look at.
Thank you.
Good, wonderful. Yeah, I think very discussed and very detailed. But I think what I want is for the channel modeling, the attenuation measurements, this channel, we could have a similar situation in visible light positioning, where when we try to implement in industrial environments, we have the industrial environments are very complex. And we could have a line of sight, no line of sight reflections from that. So I think since you mentioned that you open for collaboration, so number one, we are looking collaboration in that sector. Can we characterize the channel estimation more extensively using your measurement campaign, for in the area of optical as well? And I think because in industry environment you have reflections from different metals, different robots arms. So in that area I'm looking to collaborate. Secondly, I think you're looking for short range.
We were not looking for short range.
We were measuring distances up to hundreds of meters, not kilometers. Is your model valid for the longer distances?
So the limitation is Wi-Fi.
Okay.
And LoRa was also limited. So people were saying it's kilometric, and this is not kilometric at this setting.
Okay, that makes sense. Okay, that's fine. So you're considering Wi-Fi and LoRa.
Yeah, I was considering Wi-Fi and LoRa.
Just one comment that you made, Charles. There is a fundamental difference between the Wi-Fi world and optical world in terms of when it comes to multi-pass. This is very important to recognize. In light domain, you only consider the first reflection. Anything beyond that, it is insignificant. Therefore, the contribution from the second tier compared to the first reflection is so small. Therefore, practically, we ignore it. You can do the measurement, but you gain nothing. In other words, you're basically going to work on the margins of the system. So, whereas in RF is different thing. Yes, you can look at many reflections as well, but optics, mainly the dominant was the first reflection. After that, the power drops so rapidly. Therefore, there is really no point to a lot of it. I've seen one paper that I think it was journal papers, and these guys looked at 100 reflections of light, and it's just, it's almost like, eating a food and chewing it for 2 hours. I mean, this is.
Yeah. Yes, I also like this model because it's simple.
Yes.
It's just, that's the idea of the
That's the
model.
beauty of it.
Yes. What I can say to complement this discussion is, so at the beginning, no one believed that we are going to see the second ray. No one. No, everyone was saying, hey, this is Wi-Fi. This is very robust. You have a second reflection. You have many reflections. You just see always the one, and this is going. You're not going to see anything. And this is a proof of we're seeing it. And from the other comment is, yes, there are reflections that we didn't expect to have an effect. For example, the reflection of the vehicle in the same vehicle. So this is the continuation of our work. So it's related to the two things that we're discussing. So the reflection point can be over the water, or can be here, because this is just very small, it's 17 centimeters. And we were seeing that there are changes it's seen when the reflection point changes. So if the reflection point changes and is over the vehicle, we also have a method there. I don't know in the visible light communication. Maybe there are like surfaces that are like, I would say, shiny. Maybe those surfaces could make an effect. I don't know if water. I am not in the domain, but I'm curious about to read and to see what happened. What is difficult in this kind of research is the experimental part. It's you have idea, you have model, you test, and then how am I going to get this in real? So we were lucky to have this collaboration. The collaboration in France, we're also lucky because the guy there that is working in the real time has a company that they are doing smart marinas. So he has yacht, buoy, and I have traces now. But but traces are not like this. Traces are like more on the side that the channel is changing always. I don't care if it's changed because of 1 centimeter or 2 centimeters of the water level. So, but still, experimental part, I would say that it's difficult. Equipment is very expensive. Funding for the initial year is not enough for buying this kind of vehicle, for example. So I try to do my best with what I have, with the collaboration with the partner, but yes.
Additional question? No. Thank you, Miguel. But yeah, a couple of questions. First of all, you mentioned that there is a moving vehicle, right, in the water. Was it fixed at a fixed speed or changing? And what were the effects of this speed? It wasn't clear to me. And the second point is, you did most of the experiments in Europe. And you know, in Chile, we have a lot of coast here. Have you considered testing this in Chile as well to see if there are some differences?
Yeah, thank you for the question. Well, the first question, the speed was not an issue because it was like relatively slow for the dynamics. So if it's 1 meter per second, I guess. This was an autonomous vehicle, so you can fix the target speed. So the speed was not the issue. It was the moving and the direction. This has the radiation patterns. We would like to see how these radiation patterns are in an anechoic chamber, match this anechoic chamber of the vehicle with the real things. And about the second question, we did experiments over estuary waters. Was a seaport. We have experiments in another kind of river, a channel. We didn't and fresh water, salt water. We didn't see that much variation in terms of still theoretically it might be a difference. What I would say is also interesting and is little explored and as this effect. So the water, the reflection in the terrain, is related to permittivity. So how to track permittivity? I didn't track permittivity. I just assumed the basic values, and it looks like there is an effect of permittivity in LoRa, which looks like no one is taking care of this, and we are seeing. So I would say that physical things that typically have more impact in community, and there are still few things that could be explored. So thank you.
No more questions? Okay.
Thank you. Thank you, Miguel, for your interesting presentation. And thank you very much.